Hello, this is Dr. Jabbour, and today we're going to talk about compounds and chemical bonds. Basically, we're going to learn about the bonds that can form between atoms to form these compounds. All right. So in the previous lecture, we talked about elements and how within one element there could be several different atoms, but they really are all of the same element. And the example that we had talked about was carbon, carbon 12, carbon 14, and the other types of carbons. They're all different atoms because of their atomic mass being different, but they're all carbon. So that's the element of carbon. So two or more elements, when they join together, they form a compound. So a compound's characteristics are usually different from those individual elements. And I believe in that lecture on elements, one of the examples were a sodium by itself is a metal, chlorine by itself is a gas, and when they're combined together, it forms your table salt. So it really, when they come together, they really form a new structure that has its own physical properties. So the atoms in a compound, they have to be held together by what we call chemical bonds, and that's how they come together. They form bonds between each other, and that's what holds them together, and they form this compound. So let's see what's kind of the difference between the word molecule and the word compound. It's one of those things that, can be confusing, just like people confuse atoms and elements. So we use the term molecule when we have two or more atoms of an element joined together. For example, hydrogen or oxygen gas, those are molecules composed of only one element each. So the element of oxygen, and we just happen to have two of these atoms of oxygen combined together, and it forms a molecule. A compound is a molecule with two or more elements. For example, CH4, H2O, that would be a compound because not only so it's a molecule because the bonds are formed between atoms, but here the atoms are actually of different elements. Carbon element and the hydrogen element, those are different elements, and they come together to form this compound. So a compound, we use the term compound basically when we're bringing different things together. So it's compounded, I don't know if you're familiar with that use of the term compound. Okay. So I'm not sure I really should have put this particular sentence over here because we have two different elements in the water molecule. We have the element oxygen and the element hydrogen. We really wouldn't consider that a molecule. So, actually, I'm not sure why this is here. So compounds are, so compounds are molecules, except that they are made of different elements. So maybe that's why this was mentioned here. But really it should just have been kept over here. Okay. So the number of covalent bonds that are going to happen between these elements, it will depend on what the elements are, because certain elements will require 2 electrons, other elements will require 4 electrons. So it will depend on which element we're talking about and what are the requirements for this stability to be achieved, and the seeking of these electrons to fulfill those valence shells. So we talked about that in the previous chapter. So how many covalent bonds, it will depend on how many electrons need to fill the valence shell. So depending on how many electrons we need to either bring in or pluck off to kind of get to stability, this will determine how many bonds we need to make with other elements. So it can be just simple bonds, but double bonds as well, or triple bonds. So that's the example I had used in the previous chapter. Sodium by itself is a metal, a chlorine is a gas. We combine them together, you actually end up with salt. So this is an ionic salt. And you know what? I'm going to take the time to kind of explain how we end up with that salt. That way we review a little bit about those valence shells. Okay, so hopefully I remember what the atomic numbers are. If I remember correctly, atomic number of sodium is 7, 2, 5. Oh, goodness. I always blank on these. Do we have a... Okay, so of course I'm blanking. Okay, well, you know what? I'm going to so sodium, I know is going to so it must have 8 and then one more. Okay, so the number is 11. See, I know what the result's going to be, so I can actually figure out what the atomic number is. And chlorine, 2, 8, and 7. So what is that? 10, 17. Okay, there we go. You see? So, okay. So sodium has an atomic number of 11. So 11 means 11 protons, and we learned in the previous chapter, 11 protons positively charged subparticles. That also means we have the equivalent number of negatively charged subparticles. So we have 11 electrons. We learned in the previous chapter, these electrons are distributed along orbits, different electron shells around the nucleus of the atom. And each shell only can have the capacity to hold only certain electrons. So the first shell is 2 maximum. The second shell is 8 maximum, and same with the third shell. Okay, so each shell can hold only up to 8 after the first shell. All right, and then we also learned in the previous chapter that atoms will want to have a full valence shell to get to stability. And the valence shell is whichever the last shell with electrons, flying in it. So in this case, the valence shell is that third shell with the one lonely electron over here. And remember how we distribute electrons. We put 2 on the first shell because that's the maximum we can put, which means 11 take away 2. That means we still have 9 electrons to worry about. We know that the second shell can take up to 8, so we put 8 out of those 9 leftovers on the second shell, which means we have 1 more to worry about. That means we have to go to the third shell, and that electron is just going to orbit by itself in that third shell. Okay, so we have 2, 8, and 1. For chlorine, with an atomic number of 17, now we have 17 electrons to worry about. So we put 2 in the first shell, 8 in the second shell, that's the maximum. And what do we have left? 8 plus 2, that's 10. To go to 17, that means we have 7 more electrons to worry about. Well, they go on the third shell, and that shell is not even full. So they're there on this, the 7 electrons gravitating around the nucleus of chlorine and on that third shell. Okay, so these third shells right here, this is number 3, number 2, number 1. These third shells, they basically are the valence shells, because that's where we have the last electron for these particular atoms. So these shells are not full. So that's not stable. And these atoms will have a tendency to want to have these shells full. So in order to have a full shell, sodium will have to acquire 7 electrons in order to have 8 electrons in this valence shell. It can do that, or it can also get rid of this electron over here, get rid of it. And if it gets rid of it, the previous shell becomes the valence shell, and it's already full, so it's perfect. And it's easier to get rid of 1 electron than to try to acquire 7 electrons to become stable. On the other hand, chlorine already has 7 electrons on its valence shell. So the valence shell is going to stay the shell number 3 for chlorine. And all chlorine needs to do is acquire 1 electron from somewhere. That way we have 8 electrons in that third shell. That's the maximum number of electrons. That becomes a full shell, and chlorine is satisfied. It reaches stability. Okay, so you see how these two are going to be really best buddies, because one needs to ditch an electron, the other one would love to find an electron somewhere, and that's exactly what's going to happen. So sodium atom will lose its electron, and actually, here I'm going to write from sodium, and give it to chlorine, which it will acquire it, and now have these 8 electrons on its valence shell. Okay, so with 8 electrons on the valence shell, and 8 electrons on the second shell, and 2 on the first shell, this chlorine ends up with a total number of 18 electrons, right? Because we have 1 more, 18 electrons total. So 18 electrons, that's the case after, acquiring the one from sodium, but it still has 17 protons in the nucleus. So that 17 atomic number over here, that doesn't change, because that represents the protons. Remember that. The protons, this atomic number tells us about the number of protons. We have 17 of them. That doesn't change. So for this particular atom that acquired an electron from sodium, now it has 18 electrons, but still only 17 protons. So this shows us that we have now 1 more electron than before, and that puts chlorine into kind of a new category called an ion, because it has 1 more electron than the original atom. So we put this negative sign up here to show that it has 1 more electron than it has protons in the nucleus, because it has 18 electrons kind of gravitating around versus 17 protons in the nucleus. So this is a negatively charged ion, or we also call it an anion. For sodium, what do we have? We have, we lost an electron. So now what do we have left? 8 plus 2 is equal to 10 electrons. And according to the atomic number, we still have 11 protons in the nucleus. This is not changing. So 11 protons, but only 10 electrons. That means that sodium has one more proton than it has electrons. So we put a little plus sign over here to show that this particular ion, this is a positively charged ion, this plus sign just tell us that this sodium lost an electron and ends up now with slightly more protons than electrons. So this is called a cation or cation. See, the T looks like a plus. So if you forget cation versus anion, which one is which, think of the T. The T looks like a plus sign. That's your positively charged ion. And N over here, N is like negatively charged ion. All right. Okay, so this was kind of like a sidetrack for a very important review. I think this was not in vain. This is a good review of how we distribute the electrons in the electron shells, and then how we end up needing to either pluck off an electron or acquire an electron from somewhere, and how this happens between these two, so that we end up with sodium chloride salt. This is called a salt, because this is basically an ionic bond. And ionic bonds are not strong. These ions really kind of like separate from each other very easily. Okay. So what's going on? You know, how are we able to get these electrons kind of like off of one and go to the other? It's because these electrons are moving and they have energy in them, and they're on these different shells around the nucleus. So we call them levels, energy levels, or shells. And the one that is the furthest away has a lot of energy and can kind of basically come off. So this is an example of two electrons in that just first shell. Yeah, so this is just a general drawing without specifying what this is. And the analogy that's often given is a ball bouncing down a flight of stairs. It provides this analogy for energy levels of electron. Once the ball kind of goes down the steps, it really kind of doesn't stop. It just kind of keeps bouncing down as the gravity takes it down. And this is what's going on when the electrons are basically going from one shell to the next, where the outermost shell, I'm going to say outermost and not third, because we never know which one is the outermost. Some of them are just going to be filled to the second one. Some others are filling the third one. So the highest energy level would be on the valence shell. And then the next highest would be the one below it, and the one below it, and the lowest would be the one closest to the nucleus. So the first shell. Okay. So these different shells, it's basically a different state of potential energy. In every shell, the electrons have energy in them. And the higher up the shell is, the more energy that electron has. It's kind of like if you drop a ball from the height of 10 stairs, it's really going to bounce down quite a bit. And you have that potential energy that's being basically used up as it bounces down, as opposed to if you just put that ball on the Second step, and it just kind of rolls out, you end up with kind of just a bouncy bounce, and that's it. So you have a little bit less energy if you're coming from lower level. Okay, so this in the original PowerPoint, this actually comes off and it reveals the structure, but I forgot to kind of erase this before I saved it as a PDF, because this is what I'm using here. Those are PDF files. So I can't really take this off, but I'm going to just draw it since this is what's required here. Draw the complete anatomic structure for hydrogen. So hydrogen has an atomic number of 1, and carbon, it's 4, 5, 6. And oxygen, I think oxygen is 8, 2, 6. Yep, it's 8. So I'm not worrying about the atomic masses of these different atoms. I'm just kind of looking at the atomic number. There's the atomic number. This is the atomic number. All of these. Atomic number, I'm reminding you, it's the number of protons, and we can infer that this is also the number of electrons, only because atoms are overall electrically neutral, and if we have so many plus charges in the nucleus, then we're going to have the equivalent of negative charges gravitating around the nucleus. Okay, so if we have 1 electron, let's just keep to black. Here's the nucleus. And I just drew the first shell because we're really not going to need any other shell. And here's your electron. There it is. Only 1. Okay. Let's draw carbon, and then we'll talk about how different it is. So for carbon, here's the nucleus of carbon. And I'm going to draw 2 shells, 6 protons. That means we have 6 electrons. Let's distribute these electrons across the shells. We can only put 2 max on the first one. What do we have left? 6 and take away 2. We only have 4 left. 4. Great. So the valence shell, which is the last shell filled, happens to be shell number 2 for carbon, because that's where we stopped. Okay, let's do oxygen. Oxygen has an atomic number of 8. So 2 on the first shell. And how many do we have left? Is 6 on the second shell. 6 plus 2 is 8. That's the total number. 6. Okay, so this is the distribution of electrons across the different shells for 3 examples: hydrogen, carbon, and oxygen. Okay, so let's look at stability of these atoms. Is hydrogen stable with its 1 electron on that first shell? Pause the recording, think a bit about the answer. What could it be? What could it be? And then you'll come back to me telling you what it is. Okay, so take the time to pause it and think about, okay, is this stable? Why isn't it stable? How does it become stable? None of these are stable because the valence shells, their respective valence shells, are not full. Here, the valence shell is the first shell because there's nothing else, and it has 1 electron, but we know that the first shell can take up to 2. So this needs an electron from somewhere else. How many? 1 is enough because this is maximum of 2. We already have 1 electron. We only need 1 more. Okay, let's look at carbon. Carbon is not stable. Carbon has 4 electrons on its valence shell, which happens to be shell number 2. this is 4 away from 8, because shell 2, 3, and 4, they need 8 electrons to kind of become stable. So for carbon is going to require 4 electrons to become stable. Okay. Let me go back to this. I just want to color code in pink instead. Okay, so let's write down here that there's this 1 electron and we need a second one. And we're doing it at the second one in pink. Okay, so for oxygen, we're here at 2 on the first shell, 6 on the second shell. Total number of electrons is 8 to worry about. So here, this is how we distribute them. 6 is not a full shell. Remember, the last valence shell has to have 8 maximum. So 6 is not the maximum. So oxygen will want to acquire 2 electrons from somebody. So what this tells you is that hydrogen can form a bond with another molecule just for the purpose of getting its electron that it needs. So hydrogen and carbon are going to really bond a lot together because hydrogen requires 1 electron and it has an electron to share with somebody else. So this electron is actually going to be shared with carbon, and there will be kind of a mutual benefit. You give me your electron, I'll give you my electron, and then we have that fulfilled. Okay, so the formation and the function of the molecules that we're trying to build, remember this is what we're talking about in this chapter, it depends on the chemical bonds between the atoms. So the end goal for an atom is to complete the valence shell to be stable or inert. Stable. Complete the valence shell. And how did we complete it? We brought electrons from somewhere else. That way we end up with 8 electrons on the valence shells. So inert means stable, means lowest state of potential energy. That's what PE means here. So 2 atoms with incomplete valence shells, they're going to react together and say, hey, I need your electron, you need my electron. How about we come together and I'll give you mine, but just sharing, you have to give it back to me because I still need it. And then you give me yours because I need extra electrons to fulfill my shell. So it's a constant back and forth between these electrons, between the atoms and their electrons. They both end up with completed valence shells, even though they didn't relinquish their electron, but they're just sharing it back and forth, back and forth, back and forth. So these interactions usually result in atoms staying close together, and they're held by these very, very strong bonds called chemical bonds. Very strong bonds. So covalent is one, ionic is is the second one, and hydrogen is the third one. So we already saw the formation of an ionic bond. Let's see how we form covalent bonds. So again, this is just a reminder, the chemical behavior of an atom depends on the number of electrons in its outermost valence shell. This is a very important concept. Atoms with complete electron shells are chemically unreactive. Atoms with, and by the way, examples, this is asking you for examples. I want you to kind of go look into your previous lecture, and we talked about when I introduced the periodic table, I showed you those gases all the way to the right, and those have full valence shells. Whatever the last shell is for each one of them, it's full. So they're very, very stable gases, very stable. So atoms with incomplete electron shells or electron valence shells are chemically reactive, and they're going to want to kind of like, boom, do it something to acquire electrons. And, most of the time it's not completely acquired, it's shared. Okay. Okay, so I'm going to show you, for example, how carbon, I don't know why it's still pink. Carbon has 4 electrons. Let's use it. 1, 2, 3, 4. So what did I illustrate here? I illustrated just those 4 electrons. Whatever electrons are on that last shell, we're talking about those guys and what do they need. So these 4 electrons, I drew them here in black. So what do they need? They need, that carbon needs 4 additional electrons from somewhere else. So where am I going to borrow an electron? Well, I can borrow an electron from the hydrogen. Hey, hydrogen happens to need an electron. I have 4 of them. Maybe I can share my electrons and then I get their electrons shared back to me. And then that's exactly what happens. So for each one of these electrons, we have the other electron that is provided by hydrogen. And we can actually have 4 hydrogens each one is providing, you see the pink electron? Each one is providing its lonely pink electron. The carbon is providing 1 out of the 4 electrons to this particular hydrogen atom. And I'm going to draw a very thin line. These 2 are shared now between carbon and hydrogen, and there's this cloud of electrons that's going between the 2 atoms. So this is a covalent chemical bond. Covalent bond. So the same thing happens over here and over here and over here. So it's very nice. Each hydrogen will get a full valence shell because it's able to borrow 1 out of the 4 electrons that this carbon happens to have available. But these 4 electrons are going to be useful to form bonds with hydrogen. So a molecule is 2 or more atoms held together by covalent bonds. 2 or more atoms of the same element. A compound would be different atoms of different elements. So here's an example of hydrogen. Hydrogen gas is actually formed of 2 hydrogen atoms, and each hydrogen is missing an electron, but has 1 lonely electron. So what can we do? Let's acquire an electron from somewhere. And how nice is it to see a partner over here, another hydrogen kind of like wandering around and not being happy by not being stable. So it's going to say, hey, I have an electron, I need a second one. You have an electron and you need a second one. Why don't I let you borrow mine and you let me borrow yours? Back and forth, back and forth. And that creates this very strong covalent bond. These are bonds that need, a chemical reaction to actually break them apart from each other. They're very, very strong. So we talk about single covalent bond when it's just 1 pair of electrons that's going back and forth, back and forth. So this was like the simplest example over here with just 1 pair of electrons that's shared across the 2 atoms. So for oxygen, we have basically the molecule of oxygen, and I want to show you here how this is really beautiful. So what did we say about oxygen? Let's kind of open this so it's more handy. There we go. Oxygen has 6 electrons and really only need 2 more. 6 electrons, only need 2 more. So let's draw these 6. Oh, where was I? Maybe I must have been here. So I'm only going to worry about the 6. So here's my oxygen. I have 1, 2, 3, 4, 5, 6. So when we have pairs of electrons, we don't have to worry about stability. And these two are not paired. I mean, or you can pair them together, but we would still be missing the 2 electrons that will make this more stable. We need it to be 8 electrons. Remember, we need to fill that valence shell. So here we're going to have the need for 2 more things, something else. So if we were producing compounds, we would add a hydrogen atom, which is providing its electron, and then oxygen is providing 1 electron to one hydrogen and another electron to the other hydrogen. And look at this beauty. This is how you end up with covalent bonds between oxygen and hydrogen. And here you go, you have a water molecule. So here, what they're asking you to do in this particular diagram, actually, there's nothing being asked here. I'm just showing you how 2 oxygen here can share their electrons to form this. This would be a molecule, not a compound, because those are the exact same atoms from within the same element. So I drew here a compound, and this is more of a molecule. So what do we have here? We have 2, 4, 6, 8 electrons. And so what's going on is those last 2, I'm going to actually color code this. 1 and 2. Let's say these 2. So what we need, okay. So what we need is we need an electron from the other oxygen. So remember it was 2, 6. So these 6 electrons, we need 2 more. So these 2 more electrons are going to be provided by the other oxygen, which has 2 electrons that are available for bonding. Okay, I think that's enough. So the number of covalent bonds that an atom can form, it depends on this atom's bonding capacity, which means how many electrons do we need to bring in? That will determine how many bonds we can make. So it's equal to the number of unpaired electrons required to complete an atom's outermost shell, known as the atom's valence. So hydrogen has a valence of 1 because there's only 1 electron. Carbon has a valence of 4. 1, 2, 3, 4. So if you go back to carbon here, see, we had 4, we need 4 more because we need to reach 8. So back to this, carbon has 1, 2, 3, 4. So it requires 4 more to be stable. And oxygen has 1, 2, 3, 4, 5, 6 oxygen, 6 electrons around the oxygen atom. So 6 is only 2 away from 8. 8 is the full maximum. this is stable, this is what the atom is going to have a tendency to do. So it needs 2 more electrons. So the valence is 2. When we talk about valence, it's basically how many electrons do you need so we can get a bonding. So let's talk about polarity. Covalent bonds may be polar or nonpolar, depending on how the electrons are shared between the 2 atoms. So certain atoms have some electronegativity to them, and I'm going to illustrate that when I start drawing a few of these compounds. So electronegativity is the attraction an atom has for the electrons in a covalent bond. The more electronegative, the more it sucks up the cloud of electrons towards it. So let's actually take the example of water. Here we go. Okay. What was the color coding, if it matters? It wasn't this. I think it was blue. And I drew it somewhere. Where did I draw water? I don't see it anymore. I don't remember where I put the molecule of water. Okay, I guess it doesn't matter. I can just redraw it. That's so weird. Okay. Again, I'm going to just draw hydrogen with 1 electron. So it only has 1 electron on this first shell going around and around. And then oxygen has an atomic number of 8. So it has 2 on the first shell and 6 on the second shell. 6, 7, 6, 7, 8. So that means it needs 2 more. This one needs 1 more. Okay. So oxygen needs 2 electrons from 2 partners, or or 1 partner that's going to give 2 electrons. With hydrogen, there's only 1 electron available, this black one, and it needs an electron. So what's going to happen is that oxygen oh my goodness. I thought I had clicked on the black. Here's oxygen, and here's hydrogen. So hydrogen comes with its little lonely electron. There we go, 1 lonely electron, and it needs electrons from the oxygen. So the oxygen goes, sure, I have 6 of them. I have 6 electrons. I can give you 1. And hey, sure, I have more electrons. I can give you 1 if you want 1 to become stable. That's great. Why is it good? Because I am getting your black electron, right? These electrons are shared. So every time we talk about sharing, we're talking about, oops. We're talking about electrons that are going to go towards the atom or away from the atom. This is what we're doing. In a covalent bond, we have shared electrons that are going back and forth. That way they can be counted for both atoms to fulfill their individual stability. So water can form hydrogen bond, or what am I saying? Covalent bonds with hydrogen atoms. Okay, so you understand here how the electrons, those 6 electrons, we need to distribute them on that. So we took 2 out of those 6 and basically involve them in covalent bonds, and the remaining 4 are just going to hang out at the edge like that. They're not going to be involved in anything because we needed 2 electrons, and we used 2 of our own electrons, the pink ones here, to share with somebody else who has an electron to give us and can benefit from the one we're giving them. So this is the back and forth I talked about earlier. These electrons are shared back and forth like this, and they stay like that, and it forms this very, very strong covalent bond. All right. Now, because you have the electrons here, kind of additional electrons on the surface of the oxygen, these electrons are not engaged in any specific bonds because we don't need them to. We already got the electrons from the hydrogen. So what's going to happen is that these electrons are basically creating this electro, this is an electronegative environment. I can write environment, I guess. And what that does is this cloud of electrons that are not useful for oxygen to, so to share in bonds with another atom. We don't need to do that because we fulfilled the bonding needs with the first 2 electrons, those first 2. And we satisfied the rule, and this is pretty much done. So these 4 electrons on the surface of oxygen, what they're going to do is that they will have a tendency, let's see if I can do this in, no. So this electron, we talk about an electron cloud. That's basically going around and back over here. But because of the electrons on the surface of the oxygen being so negative, they're attracting the other electrons towards them. It's basically, it's an electron cloud that sucks up all the electrons towards it. So the electrons that are in these covalent bonds, they spend a lot of time around the oxygen, a lot of times around the oxygen. So it didn't have to go, the oxygen doesn't have, I forgot what I was going to say. Anyway, so you end up with a slightly negative pole to the molecule because that electron cloud spends more time over oxygen, and a slightly less negative pole towards the hydrogens. So we write delta, meaning it's just a little bit less negative here because the cloud is constantly pulled towards this very electronegative pole of the atom. So the same happens over here, where you end up with a cloud that spends more time around oxygen and makes it delta negative. Okay, so these bonds over here, so these covalent bonds, right? So this is a covalent bond. But we call them polar. Polar bonds. Polar covalent bonds. This is the most appropriate way. Polar covalent bonds. Why? Because they are covalent bonds. We're not splitting. They are covalent bonds, and the cloud is more towards the oxygen, a little bit over hydrogen, more towards the oxygen, a little bit over hydrogen. All this is because it's due to those leftover electrons that are not participating in anything, and they're creating kind of like a havoc. They're like you know, like, okay, we're hanging here, we're going to have a party, let's kind of suck up the cloud towards us, and everybody's going to be kind of coming to the party. And this is what happens. These clouds are being sucked up towards the oxygen, and you end up with a slightly more negative end to this polar molecule and slightly more positive ends towards the hydrogen in this molecule. So these covalent bonds between oxygen and hydrogen are described as being polar covalent bonds, because we're going to have the electron that spends more time hovering around oxygen than actually being in the bond. So the three types of bonds are covalent, ionic, and hydrogen. So I already kind of mentioned ionic. Let's talk about covalent bonds. When the electrons of a covalent bond are shared equally, the bond is called nonpolar. And actually, that is the case for carbon and hydrogen. Why? Because we don't have any leftover electrons. We only had four. We only had four on that valence shell for carbon. So there's nothing special going on here. It's just, it needs four electrons. It has four and it needs four more. And it gets it from all of these hydrogens. And these hydrogens don't have extra electrons either. So there's no polarity to them. So you end up with these electrons shared. Let me kind of use that same color. Kind of shared equally. Like this. Oops. Etc. So this is shared equally. So when we say shared equally, there is no polarity. So I forgot what the PowerPoint was saying over here. Molecules, two or more atoms held together by covalent bonds. And basically that's how you end up with a molecule. We're going to see examples of molecule. So a hydrogen molecule is very, very small, and it's really only made of two hydrogens, and that's the only atom involved here. Two electrons, one pair, are shared in a single covalent bond, right? Like in here, I'm bringing you one, you bringing me one, it's perfect. We both are fulfilling each other's needs. This is the representation of an oxygen molecule. We did look at that earlier. Okay, and these are the slides I already covered. All right, so covalent bonds, there's equal sharing of the electron clouds. It's going back and forth, back and forth, back and forth. So the bonds that we describe as being polar are the bonds where there will be this unequal sharing of the electrons between the atoms. It's like, whoa, you're gravitating over there, the same as over here, the same as over there. No, 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 no. We need you all towards this side because we're very negative here and we could use some of that motion with us. So ionic bonds, like we saw previously, it's a chemical bond resulting from the attraction between oppositely charged ions. So you would have to charge the ion and then bring it back over here to participate in an ionic bond. So compounds formed by ionic bonds are called ionic compounds or salts. So this example of a salt is very, very neatly organized. So the third type of bond is called hydrogen bond, and this is a very weak non-covalent bond, but it has to do with the attraction between those partial positive or negative signs that I drew earlier between two different compounds or molecule. The hydrogen atom is partially positive because it's covalently bonded to a more electronegative atom. So here we go with the example of water, and there's also the example of ammonia. This electron cloud course, it stays over here, but it goes way over here, and it stays over here, and it goes way over here. Right? So you end up with a little bit positive here because this whole cloud is kind of moving towards the oxygen. So this will be delta negative, means a little bit more negative on this side than the other. So facing the positive charge of a hydrogen, for example, here, and communicating that with an ammonia molecule, ammonia has 1, 2, 3, 4, 5, 6, 7. I think I forgot the number, and I didn't draw that earlier, did I? I forgot the number of electrons. So try to do that one on your own, and then you can reach out if you have questions. All right, so I want to show you some examples of hydrogen bonds. Here we go. Here we go, and here we go. So these are amino acids facing each other. These two long helices are faced to each other by their, why did I say amino acids? Nucleotides. I think I said amino acids. Nucleotides that are facing each other and forming hydrogen bonds between each other. Okay, so the same with amino acids. They're facing each other and they can form these hydrogen bonds between the water molecule, the ammonia, and the rest of the molecule. So there's all kinds of examples of how there's attraction of these slightly more positive charges or slightly negative charges. There's an attraction to the opposite charge. Another example of bonds, but we don't really talk about this too much, are the van der Waals interactions. They're weaker than hydrogen bonds. So they're non-covalent bonds. They just happen to be weaker. But just enough to actually allow certain animals to kind of literally crawl up vertical surfaces. Excuse me. So what we end up with is what we call dipoles, where you have a connection, but it's very, very weak. So it's not going to last. So for this example here is the example of the gecko that can actually form these bonds with the surface. And here's what's taken on a glass, and piece of glass. And yeah, so they can do this in a very transient way. Water happens to be a polar molecule with the oxygen kind of spread out like that and grabbing one hydrogen on one side, one hydrogen on the other side, and it's going to take those 2 electrons that it needs, right? These 2 electrons. So it needs them. So there's going to be bonds here where those 2 electrons are now shared equally. But it still ends up being a polar molecule because of the electron cloud that spends more time over here. The electron cloud. There we go. So water has unique properties because of this polarity and also the hydrogen bonding it can form. So really there's kind of like 2 things going on. And you'll see the water molecules literally sticking together thanks to these hydrogen bonds. And it's going to be very, very easily disrupted because these are weak bonds. So this is a great example to show you how water molecules form a sheet, and it's literally that. So what you see here What you see here is literally a sheet of water molecules, and you have just enough pressure from this insect above to kind of try to poke it through, and and it's not able to because it's kind of light enough, and it's beautiful, right? So this gives you the idea of what a film is. It's like all of these molecules kind of connected. And so we'll go more into the water properties of the water molecule in a separate chapter. But that's all I wanted to talk about here, about these three types of bonds, those chemical bonds, ionic bonds, and hydrogen bonds, excuse me. That's it. So thank you for paying attention.